Okay. Bridget.
Can you do an example of a bike question that might be on the test?
So, like, bike question. So specifically, the things that you would have to be able to do is to repeat the calculations from the bike lab. So I would probably give you any kind of data that you would have collected. I'll just give you the data. So I might give you, like, you know, something, maybe it says, you might have a table that says, like, crank 1, crank 2, and then you might have, like, axle 1, I'm spelling that wrong, axle 2, axle 3. That's probably enough to give you the idea. And this table might be, like, observed wheel rev per pedal rev. And you might have, like, something like, you know, this on there. And then you might have another similarly formatted table where I also will write, like, the teeth in here. So, like, 25, this is way too big to go for that, maybe 30. And then maybe A2 is like, 15. Oh, sorry. Thank you. And then maybe A3 is like, oh, I don't know, they got to make this work, maybe 10. So I might ask you to, like, calculate these gear ratios. So you need to remember how we calculated a gear ratio. Does anybody remember how to do that? Yeah, so it's crank divided by axle. So this one would just be 1, 25 over 25. This one would be like 25 over 15. And that's, what is that, like 1.6 repeating. And then this one would be 25 over 10, which would be like 2.5. And then we'd have like 30 over 25, which would be like 1.2. And then we'd have this one, 30 over 15, which would just be 2. And then we have 30 over 10, which was 3. Right, so that's like one thing I could possibly ask you to do. Okay with that, Bridget? You could do that. Okay? And I probably also need to tell you, like, the diameter of the wheel. Let's say that was like 27 inches or something. And then I could ask you, like, how fast you have to pedal in pedal rev per minute to go, like, I don't know, 35 miles per hour. So I'd expect you to be able to do something like this, right? This was kind of the culminating question. And there's a number of different ways you could approach this. I think in the in the bike lab we said we built like 2 ratios and multiplied them together. Like we built the, like, 1 pedal rev equals so many inches. And then we went 20 miles per hour is equivalent to so many inches per minute. And then we did like a multiplication here using these 2 ratios. So you could do it that way. So that's one way of doing it. A second way of doing it would just be in one big long unit conversion. So you could just start like 35 miles over 1 hour and just kind of do your multiply by ratios until you get like pedal revs per minute pop out the other side. So we could start by just converting like miles or hours to minutes and then miles to inches. And then I know that pi times 27 inches is 1 wheel rev. And I know from my chart, if I wanted to pick the most efficient way of doing this, I'd pick the biggest gear ratio. So that's going to be 3 wheel revs is 1 pedal rev. And then if I multiply that out, hours cancels with hours, miles cancels with miles, feet cancel with feet, inches cancel with inches, wheel rev cancels with wheel rev, and the unit we're left with is pedal rev per minute. So all I need to do is kind of multiply that thing out. So you could do either one of these two ways. It won't matter to me which one you would do. Just it would have to be clear kind of what you did there. So would I expect you to have memorized there's 5,208 feet in a mile? Yes. Or 12 inches in a feet? Yes. Or that 1 wheel rev is equivalent to 1 circumference? Yes. Would I expect you to remember the formula for circumference? Yes. Would I expect you to remember that the gear ratio is how you convert pedal revs to wheel revs? Yes. Or pi d. Yep. Is the same formula, right? Because the diameter is 2 radii. Nick? Correct. I gave it to you. That's pi times 27. That's just the circumference. So, Bridget, you should be able to do calculations like that, and then you should just be able to answer kind of general, like, non-calculation questions about the bike report. So, like, maybe you know which gear is the most efficient, or the differences between, like, the data collected in this table and this table, and talk about those sorts of things.
So which one would be
The biggest one. The biggest number is the most efficient. Lowest number would be the least efficient, yes. Okay, so that's basically the kinds of calculations you did in the bike lab, right? Now, that again, you should be able to do those sorts of calculations, but you might also just have to answer like general, like applied understanding questions about the bike lab, and I did a bunch of for instances there. Brooke? I have these feet inches with the diameter inches, or the circumference inches. Claire? Okay, so let's say we have a situation. So we're talking about writing linear function from a story problem. So let's say we have an example. Let's say Claire has a cell phone. She pays, I spelled what wrong?
Claire.
Maybe it's a different Claire. How do I know it's that Claire?
Oh, you were talking about.
Ah, ha, ha, ha. let's say she pays a $15 monthly activation fee and 8 cents per text. So we'll write a linear function to describe her monthly bill. Okay with that idea? Okay. So we have two quantities here that are of concern to us. We have the monthly bill, and then it's also going to depend on what will the amount of money she has to pay also depend on? Which has to be what? The number of texts, right? So the independent variable is the number of texts. Claire has a choice on how many texts she's going to send. The dependent variable will be the dollars that bill comes up, because that depends on the number of texts she sends, right? Okay? So it's going to be y equals mx plus b will be the form. So if she sends 0 texts, how much will her bill be? $15, because we have to pay that activation fee no matter what, correct? What does that tell you? It tells us the value for b, right? What does that tell us the value for b is? 15, right? Because what is b? It's the y-intercept. So it's, like where the graph crosses the x-axis or whatever. That's where the x-coordinate is 0. So here we found where the x-coordinate is 0. We found the y-coordinate. So we know that the y-intercept is 15. Everybody okay with how I figured that out? Hopefully that feels kind of common sense-ish, that the activation fee that you pay no matter what would be the b part. What will the slope be then? Well, that's the rate at which we get charged per text. So this is 8 cents per text, right? I'm sorry, I'm just kind of talking through my reasoning on how I'm doing this. So when I ask these questions to you guys, it's just me kind of like, how am I thinking about this in order to write that linear function to describe our monthly bill. Okay? So that's everything together. So there's my linear function then, right? Because that is 8 cents per text is exactly a slope, because it's a rate, right? So when you're given a rate in a problem, almost inevitably that's going to become the slope, if you have something per something else. Yeah, so let's do that next. Okay, so example of a question I could ask is I could say that, just to make sure this comes out right, I could say Claire's bill for last month was $17. How many texts did she send? So I could ask you something like this now. So you're given $17 was our total bill. What is that $17 representing? That's a y value. So, and then I'm asking how many texts did she send? What is that asking for? X. So I want to find the x value for this specific y value. How do I do that? Yeah, just plug y in for 17 and then solve for x. And from here it should be pretty easy. So we subtract 15 And if I divide by 0.08, I get 25. So 25 texts. Okay with that, Claire? So I could ask a question like this, where I ask you then to like use your formula to find something. Okay? Questions about this question before we move on and take something else? Okay, good. Evan, what's next? Okay. So we have, for any absolute value function, we can think about it as a transformation of the parent function, which is just the absolute value of x, so any absolute value function I can write kind of in this form, which is our general transformation form, where our a, b, h, and k do the usual things for our a, b, h, and k. So this is the idea that I'm going to use to do something like that. So for example, if I have y equals like -2, absolute value 1/2, or let's say 1/3, x plus 1 minus 4, I am just going to start by identifying my values for a, b, h, and k. So the value for a is -2. How did I find that? Well, and then my value for b is 3. Remember that this is 1 over b, so this is the reciprocal of 1/3 is going to be b. The value for h is -1. Remember, we have a negative sign in our formula, so it's always the opposite of whatever's written. And then the k is -4. So now that I have these 4 values, I can apply the rules that we memorized for the quiz to kind of describe these transformations. So the a value, I have to check for 2 things. I have to check whether it's positive or negative. Since it's negative, what does that tell us? Good, reflects across the x-axis. And then I have to check the magnitude of it. Since the magnitude is bigger than 1, that tells me that it has a vertical stretch. Now I'll go to the b value. The b value is positive, so that doesn't do anything. But the magnitude of b is greater than 3, or I'm sorry, is 3, which is greater than 1. So that tells us it's horizontal stretch. The h value is less than 0. The h just does one thing. It's going to tell us it does left or right, and then 1 unit. And then the k value is also negative. That tells us it's going to go down 4 units. So just something like this would be sufficient there, Evan. So you're just going to be basically using the values for a, b, h, and k, and then that set of criteria that we memorized for the first quiz to answer a question like describing an absolute value function as a transformation of its parent function. So they're all going to be the same way. You're just going to use the a, b, h, and k, and then your set of criteria. Nick, is this a question about this one or different? Okay, go. That's when b is less than 0. So I just, since it's, you check it for the a's and b's, you have to check if they're negative or positive, and then you check their magnitudes. Right? So you have to do 2 things. I just wrote that in there to remind everybody that you have to do 2 things, because I see oftentimes students forgetting to check both criteria for the a's and b's. Question about this? Okay, go, Mackenzie. Yeah, you should. Yeah, you should have this memorized. I don't think that I included that anywhere because I don't have the set of criteria anywhere on there. I don't. Sure, that's fine. If that'll help. It's one of those things where, like, again, from the first module, this is just right? Still just any function f of x, and just our function f of x this time with the absolute value. But it's still the same thing. It'll be the same form over and over and over again. So like if you kind of have memorized how that works out, you'll see it again when we talk about quadratics and polynomials and all these other functions. Except we lose the 1 over b frequently when we deal with these things because almost everything has the right kind of symmetry that it doesn't really matter. Brooke, can I apply these transformations? Sure, it's probably easier in terms of an absolute value function to graph it just by making a 3-point xy table with the vertex as the middle point. Sure, should we just graph this thing? Okay. So, yeah, that's all I'm going to do. So I think that this was the function, right? Let me just go back and check real quick. Yeah. Okay? So the easiest way to approach graphing this thing is I'm just going to make a 3-point xy table. What should be the middle point of my 3-point xy table? It's the vertex. And the vertex is what values? That's h and k, so -1, -4. Good. And then I'm just going to pick a value less than -1 and a value greater than -1. So maybe I pick -2 and 0 seem like just nice, obvious choices. It might have been better to pick values that would have given me multiples of 3, and then I wouldn't have to muck around with the fraction. But these are certainly fine if you don't mind dealing with the fraction. So to find their y values, what do I do next? Yeah, just plug them into x, right? So then I just simplify down. So remember, if we're simplifying, we start from the inside most and then work our way out. So I'm going to start inside those parentheses. So that's going to be -2/3 minus 4. To do that subtraction, I need to have a common denominator. So 4 is really just 12 over 3. So that's going to give me -14 over 3. And since I'm going to graph that, it probably makes no sense in writing as a fraction. That's really a decimal. Okay with that so far, everybody? Okay. Notice here that when I picked these x's, I didn't just pick them all willy-nilly. I picked them so that they are kind of symmetric about the vertex, that they're each of them are 1 unit from the vertex. I did that intentionally because if I do that, I get that y value for free. If you didn't pick it that way, could you just plug the x value in? Sure. That's perfectly fine. Or if you forget that you get that property, can you just plug the other x value in? Sure. And then I just need to plot these things. So I have 0, -4.6, -1, -4, and then -2, -4.6. So here's my graph. Abigail? Sure. Nick?
So when is it better to use this type of, like, I guess, chart, the graph, instead of a different plot, instead of the vertical? I don't know how to like, when is it better to use this where you use the vertex instead of the other one that we did?
Well, to graph an absolute value function, you have to have like the vertex in there because you need to know what each piece of the piecewise function looks like, because remember we said one of our definitions for an absolute value function was this piecewise thing. So we have to know what this piece looks like in this piece, and when they change from one piece to the other, that change happens at the vertex, so you absolutely have to have that vertex. And then you need to have 1 point on each side because each piece is a linear function, so you need to know what the piece on the left and the piece at the right of the vertex look like. So you have to have that much information. So that's really why this becomes just the best way to do it, because it's the minimum amount of information you need to get an accurate graph. Yeah. Yes. Evan. Uh-huh. So I would just look at the picture after I've graphed this now. Okay? So the domain is, reminder, the definition is just the set of all x coordinates for the function. So I have, if I start at the negative x's, I can track that down and it's going to intersect with my graph. And if I keep going across, all those x values will intersect until I get out to positive infinity, and still that intersects with the graph, right? So the domain is all real numbers are negative infinity to positive infinity. Okay there? The range is the set of y values. So if I start on the graph at negative infinity, and I track left and right, that's always going to run into the graph up until I get to this point here, and then no more y values after that are going to intersect with the graph, right? So that point there is the vertex, and it's the y value -4. So I'm going from negative infinity up to and including -4. Sure. But here's the deal. For absolute value functions, the domain is always all real numbers. So there's really nothing to do if you have an absolute value function. You just... Yep. So the range you can tell by looking at two things. You need to consider the a value and whether that's positive or whether that's negative. If the a value is positive, the domain or the range is the k value up to positive infinity. If the a value is negative, it's going to be negative infinity up to the k value, which is what we observed here, right? This was k, and we used negative infinity because the a was less than 0. So since the a is less than 0, like it's opening our graph, no, that's just a mess. Our graph opens down, so it's covering the negative infinity of all the way up to the vertex, which is the k value. If it opened the other way, you're starting at the k value and covering all the way up to positive infinity, right? If that makes sense. So you could always, even if you weren't given the graph or asked the graph, plot the graph if you feel better about looking at the picture to find the domain and range. But you could also just use kind of these rules, and you could do it without actually having to graph the thing. Carla? Oh, okay. Evan? Okay. So the tool that I'm going to use here is that I know what the general form for an absolute value function looks like. So it's this same general form before. So this is the tool that I'm going to use. My equation that I'm going to write is going to look something like this. So let's say that I have this thing. And let's say this is the point like 4, -1. And this is the point like 0, 3 or something. Okay, so here's my graph. Right away, I should be able to fill in some values for the a, b, h, and k here. So right away, I should be able to fill in the h and k because I know the vertex is the h and k, right? So in my picture here, the vertex is the point 4, -1. So right away, I can say like y equals a absolute value 1 over b, x minus 4 minus 1. Okay with that idea so far? Now, what we said was we're going to either assume that A equals 1 or B equals 1, and we're going to make that assumption depending on which way the graph opens. So when the graph opens up, we pick the A value to be 1, or when the graph opens down, we're going to pick the B value to be 1. So this is the situation we're in, right, because our graph is opening up. Like when we say open up, means like if you poured water into here, it would hold it, rather than opening down, where if we poured water on here, it would run off. Everybody okay with that idea? Okay. So we have now that the A value is 1, so I can just kind of forget about the A because it's multiplying by 1. So now I have this. Is everybody okay to hear? Now we just need to find B. And we have one piece of information we haven't used yet, namely this other point. So what am I going to do? I'm going to plug that other point in for x and y and use that to solve for B. And so I have 4 is equal to B over 4, or this, right, because it's an absolute value. I'm going to ignore this other one, though, and just worry about one of them. We don't need 2 of them. And then to solve this, I'm just going to cross multiply and divide, and I get the B value as 1. So I can say then y equals the absolute value of x minus 4 minus 1. Okay with that, Evan? So again, not too much to do. The key to doing this, though, is remembering what the general form looks like. So what should my answer look like in the end? That the vertex gives you your h and k, and then at some point you have to assume either A is 1 or B is 1, depending on which way the graph opens. Brooke? It doesn't matter. I usually just pick the positive because it usually makes your life easier. Evan? Oh, so this is just like a normal solving problem? Yes, Nick? Oh. Yes. Right, I made the note here. And I can post these notes too when I post the video, if that helps anyways. I can turn them into a PDF. I don't know what it's going to look like because it may be like all over the place. Or would it be easier saving it as a OneNote file? I don't know. We'll see what it looks like when I try to turn it into a PDF. I'm worried about like having like half a page and then it cutting off and like, you know what I'm saying? No, maybe not. Anyways. I'll figure out. I'll put it on there some way that it's maybe most viewable. And we were talking about solving then. So maybe we have like 5 absolute value, 2x minus 3 absolute value plus 17 equals 6. So it just might be a problem like this. Could be a solving. So the first step I'd want to do is subtract the 17. Equals negative 11. And then divide by 5. And you could turn that into a decimal, I guess, but I'm just going to leave it as a improper fraction since I don't have a calculator handy. Ignore this thing on my desk. I just like fractions. And the next step or you could make an observation here. What might you note here? Yeah, already we can tell this has no solution because we know that an absolute value cannot be negative, right? And that's what this equation is saying. But if you didn't notice that, you could, again, split and keep going. But that is, you could certainly say this right now and be done with it. But if you didn't notice that, that's okay. We can split and keep going. Remember that we negate the right-hand side over here. So negative of a negative is positive. And then we can just kind of keep going. So adding 3. So I'm going to make a common denominator right now. So 3 I'm just going to write as 15 over 5. So 2x is equal to 4 over 5. And 2x is equal to 26 over 5. And then we can divide by 2. I'm going to think about it as multiplying by a half, though. Again, just because multiplying the fractions is easier, so that gives me 2/5, and that one would give me 13/5. But what do we have to remember to do before we finish? Yeah, we have to check these. Guess what's going to happen if I check them? Yeah, neither one of these are going to work. So you'd say, like, no solution. Okay with that, Evan? Right. The only thing that, if this, say, all of a sudden now is like less than or equal to, the only thing that's going to change is that spot where we have to remember that the inequality symbol. Yes. So the negative happens, you change the sign, and you flip the symbol at that piece of the split. But that's really the only thing that's different until you get down to the end and where you have to look at the two graphs to tell if it's an and or an or between the inequalities. Does that make sense? Yeah, of course. Carla. Yes. So we did that at this piece right here. So again, to graph an absolute value function, you need 3 points. And the middle point must be the vertex, which you can find by the h and k. And then you just pick a value that's less than the vertex and a value that's greater than the vertex. And then you can plug them in to find the y-coordinates. Provided that you pick your x values so that they're the same distance from the vertex, right? Like these are both 1 unit from the vertex. If you do that, then the y values will be the same. If you don't do that, the y values will be different, I should say. You might ask yourself, why in the world would you ever want to pick them so they weren't symmetric? Let's just give a quick example of a situation where that might be advantageous. So imagine we have fractions here, and we're asked to graph this thing. So the vertex, that's still not hard to come up with. It's 1/3, negative 2/5, right? But now, if I wanted to pick values that are going to be symmetric here, I'm having to deal with fractions, right? It might just be easier to pick 0 and negative 1 and have less mucking around with trying to get fractions out of this than it is to do that. But if I do that, I'm going to have to find each of these y-coordinates separately. But that still might be, quote, easier than trying to pick x values that are a fractional distance apart. So that's a situation where it might be easier not to pick them symmetrically. Although you still could, and it wouldn't be that relatively difficult. I mean, you could do this, and you could still get away with getting everything to work out. Does that make sense, Carla? Of course. Evan? Sure. Let's see. So this is an absolute value story problem. when manufacturing I don't know, CD players, the output of the factory must be 10,000 units plus or minus 1,000. How many units can the factory output to make its quota? So the idea here is that so this part is the 1,000 part, and we can either be like 1,000 more, 1,000 less than that, 10,000. So the setup looks something like this. Okay. I will post